Evet, sanırım başlayabiliriz. I think we can start. I'm sort of presenting on behalf of our colleagues Selahattin Akalp and Ferit Yardımcı. They took the building number 2 and they did their own design work. So I'm just sort of conveying their message, their slides. Bina 2 özelinde bu binayı yapan arkadaşlarımız Selahattin Akalp ile Ferit Yardımcı. Selahattin Akalp Boğaziçi Üniversitesi'nden mezun olmuştu. Doktorasını aldı. Şu anda doktor öğretim üyesi. Ferit Yardımcı ise benim şu anda halen doktora öğrencim. O da herhalde 1-2-3 aya kadar bitirecek. Bu arkadaşlarımız bu ikinci binanın tasarımını yaptılar. Slaytları biz İngilizce olarak hazırladık ki misafirlerimiz en azından hani slaytları okuyabilir uzaktan. Ben de Türkçe sunacağım ama ara ara İngilizceye de döneceğim. Evet, bizim tabii ki bu tasarım objektifimiz bize verilmiş bir bina var. Bu bina özelinde binanın bir takım tabii ki düzensizlikleri de mevcut. Onları düzeltmeden yani binayı aynı şekilde alıp bu binayı bir şekilde tasarladık. Daha doğrusu tasarladılar diyelim. Kredi onlara ait elbette. Bina 9 katlı. Burada bazı düzensizlikler var. Bunların başında gözle görülür düzensizliklerden bahsediyorum. Çünkü bir şekilde kirişlere saplandığı bir plandan bahsediyoruz. Dolayısıyla ve aynı zamanda da tabii ki simetrik bir sistem pek değil. Bekleniyor tabii ki bu burulma düzensizliği. Onun dışında bir de tabii ilk kat, giriş katı, zemin kat diğerlerine nazaran daha yüksek. Şimdi burada da bir yumuşak kat olayı olabilir. Bunlar bu tip bina özelinde, tip bina olarak ülkemizde yaygın şekilde kullanılan bir plan aslında. Yani ilk katta işte market, dükkan, işte otogaleri gibi yerlerin olduğu. Üst katlar daha tabii rigid. Hatta ilk katlarda biliyorsunuz işte dükkan olmasından dolayı pek böyle hani duvardı falan onları da pek istemiyoruz. Bir ileri daha gidelim. Kolonları da kesme eğilimimiz var. Dolayısıyla böyle bir bina stokundan bahsediyoruz. Plandaki bu şeyler, görüntü, normal kat planımız bu şekilde. Ortada bir C şeklinde bir perde duvarı var. Asansör şaftı olsa gerek ve merdiven olan yer. Bir de enteresan bir işte aşağı yukarı 45 derecelik 4 adet perde duvarı. Kolonlar fakat tabii kirişe saplandığı bir sistem de var. Diğer sağ taraftaki de gabariyi gösteriyor ki I try to also indicate in inches and also in meters. So you can probably visualize the dimensions easily. The first floor has 3.65 meters. A typical sort of building stock where you have all the grocery stores and other sort of means are usually there. So they tend to have a higher story height, and others are regular floors, 2.7 meters, around 2.7, 2.9 meters or so. So this is a typical building stock. Evet, burada biz özellikle işte 30 megapascal, bir evvelki binada 40 sanırım kullanıldı. Burada biz 30 kullandık. İşte 420 megapascal'lık bir donatı. Düşey yüklerden de zati yük olarak 11 ki daha bir evvelki binada 7.2 kullanıldı. Biz 11 kullandık. Canlı yükler 2. Bir de tabii ki işte bu sismik mas olarak da bildiğimiz gibi 0.3 katsayısıyla canlı yükleri çarpıp bir sismik mas da elde ettik. Şimdi sağ tarafında da ETAPS'la analiz edildi. This building was analyzed with ETAPS. And here are the gravity loads, although I think Professor Barbosa and our previous colleague, they used 7.2. We had 11, so we used 11. Others are trivial. And the ETAPS model also is followed, as you can see on the right-hand side. Also, according to our code, we have stiffness requirements. So we have effective stiffness table. Bu tabii ki bizim şartnamemize göre, bu tablo zaten şartnameden alındı. Burada işte efektif tabii ki rigidlik katsayılarımız var. Bunları da kullanmak durumundaydık. Bunu da geçelim. Yani bu arada tabii ki döşemeler shell elemanı olarak hesaplandı. Ve bunların tabii ki belli oranda da bu rigidlikte etkin rigidlik katsayılarıyla da çarpıldı. Evet, significant amount of beams are indirectly supported. Burada tabii kirişe saplandığı bir durum var. Epey o planda da görünüyordu zaten. Dolayısıyla torsional, so we have torsional stiffness as well. Due to these beams originating from a column and ending up at another beam. So we don't have a column-to-column sort of connection in most cases. So you may expect some torsion as well. So compatibility torsion could be a method which we can use in the modeling. And and full rigid, yani rigid beam column joint, yani bu kolon kiriş bölgelerinde de rigid bir joint tahmini yapıldı. Again, according to our code, we classify our buildings. Burada da daha evvelki sunumda da anlaşılacağı gibi bunları da zaten hani pek açıklamak, ayrıntılı açıklamak da doğru olmaz. Burada BKS 3, DTS 1 ve BYS 5 olarak binamızı bu şekilde tanımlayabiliyoruz. Şimdi kuvvet bazlı yöntemde iki metot olabilir. İşte bir eşdeğer statik yükleme, yatay yükleme. Bir de mod combination, birleştirme yöntemi. işte burada tabii ki 20 mod'a kadar olan bir analiz yapılıp bunların birleşiminden bir şekilde hani işte biliyorsunuz bu %100 olmasa da işte %95'e kadar olan bir şey var, bir birleşim var ki bunlarda da onu gördük. Birazdan onu da söyleyeceğim. Spektrumu da burada tasarım spektrumu olarak bize verilen Denali spektrumunun bir çizimi. Aşağıdaki değerler, SS, S1 değerleri biliyorsunuz bizim işte haritalardan alınan yani bölgesel veya koordinata özel değerler olmakla birlikte bu Denali depremine uydurulmuş yani bir deney yanıyla bulunmuş bu parametreler, köşe periyotları ve bunlar SS, SL, S1 daha doğrusu ZC için bu değerler araştırıldı. Yani bir haritadan bakılmadı. Onu demek istiyorum. Tabii burada da bir we also have a reduced seismic forces. We take R equals 7 in this case, as you mentioned 8 in your previous building. So 7 is a probably a good number for ductile dual system. We call it shear wall and frame system. And this is the reduced spectrum. And then we have load combinations. So we also use 5%, 0.5% of the eccentricity limits. And then, of course, the first step is to check the irregularities. So our code also defines plan and longitudinal along the height irregularities. We can spot two for this building, torsional and soft story. There are some empirical formulas to check whether we have these irregularities. Tabii bu düzensizliklerle ilgili de bir kontrol yapmamız gerekiyor. Dolayısıyla bu bina üzerinde torsional ve soft story ile ilgili A1 ve B2 düzensizliğine önce bir bakıldı. Burada torsional olarak işte hepimizin de bildiği artı eksi 5 eksentrisiyle çalışalım. Buradaki oranla, eta oranıyla ki bunun da 1.2'den küçük olması gerekiyor tabii ki torsion olmaması için ama tabii 1.2'den büyükse burada bir torsion olduğu saptanıyor ki hesaplarda 1.34 çıktı. So we found out of this ratio 1.34 in our analyses. So this value is limited to 1.2. So long as you have a number less than 1.2, you don't have that irregularity, but we do have 1.34. But 1.34 and 1.2, I mean, one can discuss also why 1.2. As Professor mentioned yesterday, probably this is another democratic sort of pick number. But according to the code, again, we have a torsional irregularity. As far as the soft story is concerned, again, at this check, although it seems we have a soft story, but at this check, we don't have, again, that number, magic number 2 against 1.42. So once we carry out all the checks, then we can sort of estimate our interstory drifts. Bu tabii ki göreli kat ötemelerindeki hesaplama hepimiz biliyoruz. I think yesterday we discussed with Professor Barbosa about 1.6% and 8%, 0.8% thing. So here we use 0.008 or 0.8% criteria because we have infill walls and those walls are attached to the frames. So therefore, we tend to use 0.8%. Otherwise, our code describes if you have, let's say, walls and then some styrofoam maybe in between, and then the columns and the beams later on. So those are not connected, supposed to be not connected. So therefore, we can use 1.6. But in this case, we can check with 0.8. Yani 0.8 ile biz bu kontrolü yapıyoruz. Burada tabii ki bir işte kapa değeri var. Dolayısıyla bu tabii ki lambda'yı bulmamız gerekiyor. So lambda is defined as a ratio, acceleration ratio between DD3 and DD2 earthquakes. But then since we didn't have a specified location, so they decided to choose, in this case, I mean, it's not the whole design process because we normally have a specific location, specific coordinate, but in this case, it's up in the air. So we chose 10 different locations, and then we try to estimate lambda. So burada tabii ki tam böyle bir koordinatımız olmadığı için arkadaşlarımız diğer tabii binanın da değişik olması, değişik bir hesap yöntemine girildi. Yani sadece lambdayı bulmamız için bir 10 değişik yine yüksek sismik bölgesinden 10 değişik bölge seçilip oradaki lambdaya bakıldı ve onun ortalaması alındı. Yani sadece bu örnek için tabii ki. Dolayısıyla böyle bir lambda değerleri hesaplandı. Bütün bu şeyler için, değişik koordinatlar için. So like I said, we chose 10 different locations, high seismic locations, and when you calculate the lambda values, then this is a typical plot or the variation of lambda, let's say, and then we can easily calculate an average lambda or 1 over lambda in this case, which is 3. So we use that value. Instead of using one specific location, we used 10 specific location and we average that. And then the drift limits, or the drifts actually, not the limits, but the drifts, including 5% eccentricities, look like this in the Y and X directions. So we reached about 2.5%. Ours is 2.4, but according to ASC, as our professors indicated earlier, I think 2.5, but I think you said 2 also, 2%, I think the new limit. Yes. And again, as far as the R factor is concerned, we chose 7. And according to ASC 7, the CD value would be 5.5 in this case. The mass participation ratios also were analyzed bu model analizlerde. Birinci modun first mode turned out to be torsional, and tabii bu pek istenmeyen bir şey yani bir değil mi? Boğulmayla ilgili pardon şeyimiz modumuz birinci moddan pek hani olmasa da daha iyi olur şeyimiz var. İkinci ve üçüncü zaten X ve Y doğrultusundaki modlarımız. Toplamda da %95, %90'lara ulaşan bir ki X8'de yani 20'ye kadar gidersek zaten daha da yükselebiliyor. Dolayısıyla böyle bir sonuç da elde ettik. And then all these parameters were calculated, namely base shears in X and Y directions, overturning moments, and so according to mode combination and also equidolateral static load. So all these values are computed, so I don't have to repeat them all. And then, as far as the final design is concerned, so we just skip this. The beam sizes were chosen as 300 by 500 millimeters. So the only beams with both sides are connected to vertical structural members. I will explain that. Contribute to lateral stiffness of stiff. Yani bazı bir takım kirişler de çünkü bazı kısa kirişler olduğu için orada kenarlarda onu da birazdan planda göstereceğim. Onlar da 400'e 700 olarak ortaya çıktı. Buradaki kirişlerimiz işte yeşil renkli yani kirişlerimiz 400'e 700. Diğerleri ise işte 55'e 50. Köşelerdeki yani bu binanın dışındaki kirişlerde de 30'a 50 olarak meydana çıktı. Ortada da bir there's a wall C shape or U, so depends where you look at it or how you look at it. There's this shear wall in the middle and other columns surrounding. So these are the color-coded beam and column also dimensions. C for column and B for beam. This is for the normal floor. Obviously, between the first floor or the ground floor and the normal floor, we have about 1.5 meters of extensions. So the normal floors are area-wise bigger than the ground floors. And so obviously when you go to the normal floor level, you will see these columns inside the apartments. Although şunlar pek okunmuyor gerçi ama buradaki fracture reinforcement ratios are there. It's about 20%, anywhere between 1 to 20% or so. We can identify them. Just we picked one, just the third floor, for instance. Again, here 1%, almost 1% or 1.2%. The beam fracture ratios. These are the column fracture ratios. Kolonlardaki bu donatı oranları da burada var ki bunlar da aşağı yukarı pek okunmuyor ama 1,5 hatta 2'lere kadar gidiyor. Yani 1.5, between 1 and 2, let's say. The numbers seem to be smaller in this screen. So, the third floor also was analyzed. And then the shear reinforcements are there. So I will skip those things. Beam shear reinforcement also was calculated. And then finally, the C-shape wall was designed accordingly. So this was the end of our design procedures. The main thing was, of course, maybe this slide will explain the base shear values, and then, of course, the drifts, 2.4. I think this is it. So if you have any questions, I'll try to answer them. So this is the end of the slide. Thank you.
When I look at the structural reinforcement ratios at the third floor, these are for the beams? These are for the beams.
Beams, yes. The upper and lower, the upper and lower reinforcement ratios.
Yeah, top and bottom.
Top
of
and
the
bottom,
beam, yeah.
yes.
Did anybody check to see what the base shear result would be if you just took the capacity of the beams?
I don't think so. No. Yes, bunlar üst ve alt donatı oranları.
So if you size the beams and size the columns, was there any estimate of what the period of the building might be?
The period of the building, I think it wasn't specified here, wasn't it? Because I don't think the period was also indicated in this. It was calculated, but I don't remember what the periods were, and but I have to make additional inquiry about that. It should be in the report actually. Yes. Yes. Tablo 4.
Yeah, one.
Şimdi hatırlamıyorum yani şeyi. Evet.
1 second, the next, and 0.9. Well, no, the first was torsion, you said. So 0.9.
0.9 gibi evet. Olabilir.
Around 0.9.
09?
Yeah.
Yeah. Şurada da yok galiba. Buraya dahil edilmemiş sanırım. Ha burada pardon evet. Onu görmedim evet. 0.9.
Calculated period was 3%. 3.
Şu 0.9 civarı. Evet. Şu ikisini alacak olursak. Yeah, the first mode is torsional mode. Bendings are second and the third ones.
I have a general question, mainly for me to understand. I heard that this design was, not the design, the geometry, more or less, was a building that actually collapsed.
Actually, the original version of the building collapsed in the Samos earthquake in Izmir. Okay. And the general, sorry.
Mikrofonu alabilirsiniz.
The original version of the building collapsed in Sisam earthquake. The building was located in Bayraklı region in Izmir. The general geometry of the building is given to the engineers to use this system to generate the code-compatible structural design, and the dimensions of shear wall, columns, and beams are representing the current practice of seismic design code of Turkey. Now, we know we got some data from the demolition of the building. The reinforcement details, especially for the shear wall and also columns, were very weak, and the concrete quality is around probably 8 megapascal. In this current design, of course, these properties are good, compatible with the collapsed one. But now we can make some comparisons, or because to understand the availability of your procedure is convenient for this dwelling house type building. The seismic period is relatively smaller than the 1.5 second, especially they use the cracked section stiffness for the members, beams and columns, and also even shear wall. In that case, around 0.9 second at both direction in translation modes. Yeah.
Using the effective height of the second story and third story, if I use the smaller one, probably the first story would be larger, but the estimated period, the target period for OBD would be 0.98 seconds.
Mm-hmm.
So not too far from what you're getting from your ETABS model. Yeah.
Evet, buyurun Günkut Bey.
Bu esasında örnek yapı bizim özellikle İstanbul'da veya büyük şehirlerde üst kattan sonra konsollu binaların bir örneği. Ve bu binaların hepsi esasında tasarımda sakat tasarlanmış binalar. Sebebi de şu, özellikle çevre kolonları bağlayacak olan kirişlerin atılmaması. Ve bu özellikle de köşe kolonlar iki taraftan, bir sonraki hocam. Köşe kolonlar iki taraftan kirişle bağlanmıyor ve evet. Yani biz hesaplarda bunları kurtarsak bile tasarım olarak baktığımız zaman bu köşe kolonlar ve bağlanmamış, kirişle bağlanmamış kolonlar hep depremde problem olarak ortaya çıkıyor. Ve Ercan hocamın söylediği gibi İzmir'de örnekleri var ama esas Gölcük depreminde de Gölcük'te köşeleri çökmüş, bu binaların köşe kolonları çökmüş olan çok örneği var. Sebebi de iki taraftan bağlanmamış, tek başına konsol gibi çalışan kolonlar bunlar. Daha sonra bunlara çözüm olarak aynı sisteme kolonları binanın dışına alıp aşağıda bu sefer büyük konsollarla bunları taşıtmaya çalıştılar. Ama depremlerde o konsollarda bu sefer büyük problemler çıktı ve 2018'de de o yasaklandı. Dolayısıyla bu çıkmalı sistemlerden vazgeçilmesi gerekiyor ve elimizde büyük bir maalesef stoğumuz var. Bu yanlış tasarımla taşıyıcı sistem kurulduğu için. Yani mimari olarak bakıldığında tabii şimdi köşede salon var. Salonun iki tarafından kolonları bağladığınız zaman salonun içinde kiriş gözükecek. Yandaki odalar yatak odaları, oradan da kiriş geçtiği zaman odanın ortasından kiriş geçmesin diye.
Onu da asmolenle
Ama
çözüyoruz.
Asmolen bu yönde bir bakıma iyi esasında.
Evet.
Hiç olmazsa yatık da olsa bir
Gizliyor.
kirişlerle bağlantı sağlıyor ama yani neticede elimizde çok kötü bu şekilde yapılmış bir yapı stoğumuz var. Yani bunların bir an önce yeni sistemlerle donatılması lazım. İmar kanunlarında da bence artık bu konsollaşmadan vazgeçilmesi gerekiyor. Aşağıda neyse yukarıya da o şekilde çıkılmasında
Doğru.
yarar var.
Evet.
Taşıyıcı sistem olarak.
Zaten şu anda o sistem benimsendi sanırım yeni kanunla. Çıkmalı binalar yasaklandı diye biliyorum.
İnşallah.
Evet. Ama tabii ki müteahhitler Ankara'ya gittiler. İllaki çıkmalı yapalım diyorlar ama yani o sistem artık şu anda umarım tarihe karıştı dediğiniz gibi. That's right. The problem, of course, with this plan, as you can see, the columns in the normal floor levels are not connected with beams. Especially, you can see the beams on the exterior side. It's like a U-shaped beam, which is quite unlikely to, we don't want to have any sort of design work like this. But they did that design, cantilever design. Like I said, in the first floor or the ground floor, these columns are like this. So you have beams, you have the cantilevers, and then the whole building, starting from the first floor, is cantilevered. So the columns are not connected with beams, and this also posed a lot of problems during the earthquakes because we have no continuity at all, no grid system. So our colleague also mentioned this, and today, fortunately, this system was not allowed. Is not allowed. They completely changed the law, and nowadays your columns should be at the exterior of the building, and you must have also a grid system as much as you can. So this is what he commented on. Evet, doğru. Yani U şeklinde kirişler artık da görüyoruz. Çok enteresan.
So maybe a couple of questions just for me to understand, because it seems you have a lot of these buildings, existing buildings.
90+% we have this type. 90+%,
Wow.
I would say. I don't want to say 99, but
Wow.
90+.
So is the goal to try to understand the performance? Because modeling, this is a big challenge. Modeling to collapse is a big challenge. And then the next question is, once you understand the collapse mechanism, if you have 90% of your building stock that looks like this, what is the vision for next steps? Maybe it's a political question.
It is actually they enacted a new law, and according to the law, they said, like I said before, they banned the cantilever type of structure system. So all the columns, all the load carrying system must be at the exterior of the building, and all columns must be connected by beams. So there should be a grid system. But again, architectural also concerns are there because no one wants to see any beams inside the living room or bedrooms. So they go about what they do is we have this such system like a floor system with many beams. We call it asmonen, or probably in Europe, Portugal also, you may have the same system, like a ribbed slab system. So our code says, well, we're banning this rib system. And then, of course, you go around and they say, okay, but they don't say two-way system. So then we can apply two-way rib system. Now they're applying this two-way system because the code didn't specifically say you are not allowed to have two-way system. But then again, also, I think we're going to have some changes on that. So we will ban all the rib system. You can have flat slabs, which I would prefer. Also, columns must be extended at the exterior of the building. Evet. Yani şu andaki sistemde biliyorsunuz binalarda artık çıkmalar yasaklandı. Hatta şartnamemizdeki ufak bir söz, işte hani asmolenleri yasaklıyoruz diyorlar ama şu anda da biz iki yönlü asmolen demediği, biz iki yönlü asmolen kullanıyoruz. Ona da kaset diyoruz falan yani. Ama işte biraz tabii kulağımızı öbür taraftan gösteriyoruz sanki. Sanırım onu da belki de Ercan Hocam daha iyi bilir çünkü o da komisyonlara gidip geliyor. Onu da belki yasaklayacaklar. Hani benim tabii ki hani kendi görüşüm aslında artık bizim hızla bu mantar döşemeye geçmemizde fayda var. Kirişsiz döşeme. Burada yol almamız, benim kişisel görüşüm, burada yol almamızda fayda var diyorum. Hatta Profesör Barbarosa'nın da açıkladığı gibi art germeli döşemeler de olabilir. Çok daha temiz sistemler ve katta kazanabiliyorsunuz veya daha yüksek katlı, daha doğrusu daha yüksek o kirişlerinde olmadığı bir ortamda, hatta aş serbest olduğu zaman da sanırım 15 kattan sonra bir kat daha kazanabiliyorsunuz. Böyle bir sistem.
On the same page, red line in the previous example. And after that, maybe we can complete the discussions and go to lunch. Yeah. Beautiful.
Do you have any comments on the,
Do I have any comment?
on this kind of and how you would like?
Well, I would suggest to the owner to fire the architect.
Well, then there will be no architects earning money in the country.
I'm not sure. I'm not sure I understand the dimensions. I see a vertical height of 8.85, almost 9 feet.
Almost 7 meters.
7 meters.
Yeah.
2.7, 9 feet. 9 feet gibi.
So how deep is the beam?
Regularly in the regular building,
500.
50 centimeters.
50 centimeters, yeah.
25 by 50 centimeters.
Now, if you use ribbed slabs, the height would be about 35 centimeters. But the thickness of the slab itself between the ribs would be about maybe 7 or 8 centimeters or so. But this is banned like this. We no longer use that system again. So it's all architecture, like architects sort of impose the structural system rather than engineers imposing, like, this is my system, so please design accordingly.
I don't think it would be fair to suggest any changes. I mean, it's a real thing you guys have to deal with. I do wonder if the flat slab system.
It's been used, but the problem is the detailing. Some failures were occurred during the construction. So they tend not to sort of use flat slabs unless sort of approval from university is also demanded. But then using proper detailing, especially at the column regions where you can use studs, for instance, for holding the negative moments, then you can use it. But we don't have that, I guess, practice. So, but I'm sure. I mean, if you start practicing, if you start building these flat slabs, then you will see flat slabs all over Turkey. This is my gut feeling. This is my own sort of feeling that we should move on to flat slabs and not dealing with these sort of connections between the columns, beams, and stuff. So this is something else.
Well, I mean, when I look at this design, it's entirely different from this design.
It
Because
is.
this design connects every beam,
Exactly.
every column, and it's essentially a flat, thin slab,
Yes,
which gives you a period of
15 centimeters.
1.2
Yes.
seconds. When I look at this design, there's no continuity of the beam.
No.
So, in order to, like line 3 or line 6, or you have to rely on the beam going torsionally in one direction, and I don't know how you would analyze
Short,
Huh?
short shear span.
Yeah.
Really short shear span.
Well, but I mean, where is the connection between the beams going across?
It's not.
Yeah. So I don't understand how you get a period of 1 second.
Mm-hmm.
Have you? The buildings that I looked at throughout Turkey were not like this at all. They had a regular pattern of columns and beams. Here, you have to have torque on your beam to get it to the column. I don't know how you would analyze it. And I have a hard time understanding how you could get to a period of 1 second on a 9-story building. So something isn't making sense here.
Probably. You're right.
I mean, I can see a nice line at the bottom here with 5 columns and a beam.
Mm-hmm.
That would be consistent with the design of 2. But the rest of it, I don't understand how it would work. But, I mean, principally, the beam sections around the core would rely on torque in the beams. Obviously, that didn't happen. But I mean, still, on building 1, you got a period that I would find would be consistent.
Yes.
Eyeball. This, I don't see how it could be stiffer than that building.
I don't, yeah.
What I would tell the architect is on those lines where you have the diagonal columns, move the columns into line. Get them in line. So that they,
Well, yeah, of course. I mean, many things can be done. So this is an extreme example
Yeah,
which we wanted
I
to.
hope so.
Yes.
But
It is extreme, but also it's quite common. I mean, because we have these cantilever sections. I mean, cantilever sort of floor area, which is very common in Turkey. So when you get into that, then the upper floors have no sort of column to column connections. So this is a great problem. And the first building, of course, is like a perfect grid system, but this is, I think, it's more common in Turkey. That's why we are banning the cantilever system, and then sort of trying to get all the columns lined up within one axis system. So some improvements were made, obviously. Some improvements, major improvements were made.
Well, I mean, to talk with the architect and turn some of those columns so that it would act like a frame
Exactly. Yeah.
would be
Yeah.
easy. I mean, functionally, I could see no reason. If you see that column on the second line down that's turned this direction, it can't possibly function in what I would call the north-south direction because the frame is too short.
Yeah.
On the other hand, it's not going to work in the east-west direction because it's turned weak axis.
That's right. So I guess this is why it's collapsed.
right.
Unfortunately.
So I can't believe you're building anything with any kind of column arrangement like this.
Yes. But this is a typical 70s, 80s type of construction practice. 94, yes. And 8 megapascals, you said? 8 megapascals, yeah.
Yeah, what do you do with 8 megapascal? 8 megapascal would be like 1,000. 1,000. Right? 1,000 KSI.
Maximum,
Right.
yeah.
Sorry, 1,000 PSI.
1,000 PSI.
1 KSI concrete.
Well, I showed you the twirling buckets that I used.
With
And,
weights.
The city finally let us do that test, but they evacuated the whole area and let us play with our buckets. And the period started to approach 3 or 4 seconds, but the building really rocked, so we stopped. So the contractor called me back. This building was built around 1900. So the contractor called me when they tore it down. And the walls that we thought were shear walls were plaster on top of sand.
Oh.
So we escaped death by So that's probably what the problem was, partially.
Actually, just before we start the OBD version of this building, a colleague of mine asked me to ask you if you have any suggestions. Obviously, I may know the answer, but I just wanted to ask you again. The retrofitting scheme which you would sort of think about. Let's just say that you're not going to erect the building. You're not going to. What would you do? I mean, it's an 8 megapascal low load strength configuration like this. Would you be able to retrofit this building? I mean,
Well, the first thing I would do is eliminate the voided slabs. So make wide beams.
bir şey yapabilir. Evet.
So the first thing I would do is eliminate the voided slabs. You use the voided slabs, you have tiles that reduce and create these small beams that seem to go nowhere. So I would take a wide section along, take that line next to the walls there. I would make the beam as wide so that it would grab every column.
Okay.
And then I would reinforce it so that it would do so. But you could develop a pattern. You got the pointer?
Niye çalışmıyor?
I would create a beam that grabbed all of those columns.
Yes.
And I would move this column out to a big column there. Because this is a stair corridor.
Yes.
And there's no reason why it can't move into the line. The same thing with this direction. I would bring this out and join it with the beam there so that you develop a whole flat plate of systems rather than defined beams with voided slabs. You understand?
Yes.
So you'd have a continuity going across. Here, here, and the same in the other direction. The problem with the voided slabs is the beams are all discontinuous.
Yes. Evet, burada tabii kirişler veya daha geniş çapta kirişler veya hani bir betonarme kirişler ekleyip en azından bütün bu kolonları birleştirebilirsek orada bir taşıyıcı sistem oluşturabiliriz. Güvenli bir taşıyıcı sistem oluşturabiliriz diyor. Evet. Yani Niyazi Bey'in en azından sorusuna belki bir ufak bir cevap geldi. Rica ederim. Okay, so we can move to OBD of this if possible. Maybe not. Or we can skip to building number 3. Okay. Tamam.